I have everything.
Okay, then I'll be heading out. Thanks for coming, and I'm sorry if I was a little bit, late and didn't get everything done. But yeah, bye.
Okay, so yeah, well, hello and welcome everyone to today's class. And today we'll be learning some physics. And specifically, we're going to be learning about momentum. So let me share my screen and we can look at the handout for today's class. And also, for some reason, whenever I share my screen, it doesn't let me open up the Q&A. So if you have any questions, just send it in the chat and send it to panelists so I can see so I can see if you have any questions. Okay, so let me share my screen. Okay, so let me know if you can see my screen before we begin. Okay, so since no one said anything, I'm hoping that everyone can see my screen. Okay, so yeah, today we're going to be covering momentum, collisions, and its relationship with forces. And before we begin, we're going to quickly go over the concepts from last week. And if you recall from last week, we covered what forces were. And forces are basically just pushes or pulls on a certain object that cause an object to move. And we also looked over their types, such as the normal force, gravity, friction, and the spring force. And also, we covered the 3 laws of mechanics by Newton. His first law, which covered the law of inertia, an object staying in motion will stay in motion unless acted upon by an external force. The second law, which was F equals ma, which gives you the force if you have the mass and the acceleration of the object. And then the last law, which was a reaction, which said that every force has an equal and opposite force that's in the opposite direction, and it acts on a different object. So with that in mind, let's start with today's class. And we'll start by understanding what momentum is. So momentum is a strength or force that something has when it's moving. So it's basically like something that you feel, some strength that an object has when it has some velocity, when it has some speed. And this is the reason why you need to apply a force on an object for it to slow down or to make it go faster. And also momentum is a vector, meaning that it has a direction. And the direction that the momentum vector points in is the direction of the velocity vector. And basically what I mean by that is, suppose we have some object moving in this direction. So it has some velocity v. Then its momentum is also going to be pointing in the same direction. So it's going to be pointing this way. And this is going to be some momentum, p. And momentum is normally denoted by this letter p. So whenever you see p in some equation, most likely it's going to be talking about momentum. Okay, so does anyone have any questions so far? Okay, I see. What can you use momentum for? Yeah, so I'll be covering that in like a few minutes, probably, because momentum will be used in collisions, and that's pretty much the main use of momentum. You're not going to usually see it anywhere else. Mostly when two things are colliding with each other, that's when you'll have to use momentum. So yeah, that's a good question. Is there any other questions before I continue? Okay, so if there's no questions, I'll move on to the mathematical form of momentum. And mathematically, momentum can be described as P equals mv. So recall that P is just the letter that we use for momentum, like F is for force, M is for mass, like that. P is momentum. I don't know why they use P because, well, momentum starts with an M and M is not P. So but anyways, they still use P as momentum. And so momentum is equal to the mass of the object times its velocity. So how fast it's traveling. So all this equation is telling us is the faster an object is traveling, the more momentum it has. Or the heavier the object is, the more momentum it has. And this means that it will take more force for it to slow down or speed up the object since it has a higher momentum. Okay, so let me quickly let's do a few problems regarding momentum. Okay. Let me. Okay, so the next page. Okay, there it's loading now. Oh, I want to drag. Okay, sorry for the problem. Just trying to figure out why it's not working. Okay, so let's try this example about which of the following objects will have the most momentum. So you guys can try this and you can send your answers to panelists and we can discuss which one you think will have the most momentum. Okay, so someone's saying the second one. Okay, that's a good answer. Okay, more people are saying the second one. Okay, I see another different answer, the third one. Okay, more seconds. Okay, so let's go through each of them, each of the different objects and find the momentum of them. So remember, momentum is P is equal to the mass of the object, M, times its velocity. So for the first one, the mass of the book is 5 kilograms and it's at rest. And that just means that its velocity is 0. So this means that the momentum of the first object is just going to be 0. Now, if you take a look at the second object, it has a mass of 0.2 kilograms and a velocity of 200 meters per second. So when we multiply that, we get 40. For the third one, we get a mass of 120 kilograms and a velocity of 4 meters per second. And when we multiply that, we get 480. And then the last one is 70 times 6, which is 420. And out of all of these, the third one has the most momentum. It has a momentum of 480. Okay, so yeah, the third object has the largest momentum. Okay, does anyone have any questions? Okay, so before we go on, I'm just going to quickly discuss what the units of momentum are. So we know that P is equal to the mass, which has some units, times the velocity, which has units as well. And mass has units of kilograms, and the velocity has units of meters per second. So can anyone guess what do you think the units of momentum will be? Okay, yeah. So all we have to do is we just multiply them together. So yeah, the units for momentum will be kilograms, which comes from the mass. So we have kilograms times meters over seconds. So meters over seconds. Yeah, so that was not a trick question at all. All you have to do whenever you want to find the units of something, you can just find them by finding the units of like all of the other objects and multiplying it together. So in this case, the units of momentum will just be kilograms times meters per second, which in this case is kilograms meters per second. Okay, so does anyone have any questions before I continue? Okay, so if there's no questions, I'll move on. And so now I remember someone asked, what is momentum useful for? And this is what we're going to be discussing for the rest of the class, collisions. And this is what momentum is useful for, because it lets us figure out what happens to a system and when two objects collide. And the reason why it's useful is because of a special formula. And this is called conservation of momentum. And what this theorem says is that in any system just means a group of objects where there are no external forces. And external forces just means when no other forces are acting on the objects, then the total momentum of each object stays constant, or the total momentum of all the objects combined stays constant. And we can write this mathematically as a sum of all of the momentums for each object. This is equal at the beginning is equal to the sum of all the momentum of the objects at the end. So when anything happens, the sum of the momentums of all the objects will stay the same. So this basically what this theorem lets us do is if we know the initial momentum of all the objects and the final momentum of all of the objects except for one of them, we can find the final momentum of the object we don't know by using conservation of momentum. So and then okay, let's relate this to collisions. How can we use conservation of momentum in a collision? And the easiest way, let's just use two object collisions, because of course you can have like many objects colliding at once. So let's take a simpler approach and look at when two objects collide. So we have one object here and another here, and they're heading towards each other. So eventually they are going to collide, right? And then one object might be moving back this way and the other one might be moving another way, like that. So conservation of momentum tells us that the momentum of this object plus the momentum of this object, which is the total momentum before the collision, is equal to the final momentums of both objects. So the momentum after each object collides. And yeah, so that's basically how conservation of momentum can be used in collisions. First, we find out the momentum before the collision, and we find the momentum after the collision. So here's a problem showing conservation of momentum and how it's useful. So try out example 2. Okay, I'll give you guys around like 2 or 3 more minutes to try. Okay, so we have one answer. Okay, I see some good answers. Okay. So a lot of different answers. All of them are close to each other, but not all are the same. Okay, so remember, momentum is a vector, which means the direction that it's pointing in matters. So for example, what I'm talking about is, let's say that stuff pointing to the right is positive. So any vector or anything pointing to the right is positive. So let's just draw out the situation. So we have some 5 kilogram car, 10 meters per second to the right, and another one moving at 8 meters per second to the right. So let's say this is the 5 and this is the 6. Okay. And then we know that they collide, and the 5 kilogram car now still moves right, but it's a bit slower because originally it was at 10 and now it's moving at 6. And we want to find the velocity of the 6 kilogram car. So if we take the rightwards direction as positive, then the total momentum will be 5, which is the mass of the first car, times the velocity of the first car, which is 10, plus the momentum of the second car will be 6 times its velocity, which is 8. And if we add this, we get that the total initial momentum is 98. And since both of them are to the right, it's positive. So that's why both of these 5 times 10 and 6 times 8 is positive. But let's say that the 5 kilogram was moving like this, but the 6 kilogram car was moving in the opposite direction. Then we would have to put a minus sign over here because it's pointing opposite of what we're saying is positive. Okay, and this is just because momentums are a vector. So the direction matters. Okay, so this is the initial momentum, 98. And now let's try finding the final momentum. So the final momentum will be, we know 5 kilogram car is moving 6 to the right. So we have 5 times 6, which is positive. And then we have plus the 6 kilogram car. And let's say it's moving at some velocity v after the collision. So this means that the final momentum is going to be 30 plus 6v. And conservation of momentum tells us that 98, this must be the same as 30 plus 6v. So we can set 98 equal to 30 plus 6v because we know those have to be the same since there's no external forces. So if we let 98 equal to 30 plus 6v, and then we can just solve for v. So subtracting 30 from both sides gives us 68 equals 6v. So this means that v is going to be equal to 68 over 6. Or you can simplify that and you should get 34 over 3. So yeah, that's how we use conservation of energy in a collision. Does anyone have any questions? Remember to ask questions to panelists in chat because for some reason it doesn't let me check the Q&A when I'm screen sharing. So if you have any questions, put them in the panelists, send it to panelists. Okay, so if there's no questions, then I'll move on. Okay, so now we're going to discuss some types of collisions. So there's actually types of collisions that happen. When two objects collide, there's many different scenarios that can happen. And there's essentially 3 types of collisions. There are more, but there's 3 main types of collisions. And the first type of collision we'll be looking at is an elastic collision. And an elastic collision is a collision where the momentum and energy are conserved. And basically what this tells us is that we are able to get 2 equations, a conservation of energy equation and conservation of momentum. And I know I haven't talked about energy yet, but all you need to know about this is that energy uh, is basically a property of an object, and it can depend on the velocity, um, the position of the object, and things like that. So an elastic collision conserves both momentum and energy, and this allows us to make two equations: a conservation of momentum equation and a conservation of energy equation. And the importance of this is that if we know the initial velocities and masses of the objects, we can find the final velocities. We don't need to know one of the final velocities to get the other velocity. So that's why elastic collisions are cool, because there's only one outcome for every elastic collision. Like in normal collisions, you can have many different outcomes, but in elastic collisions, you can only have one outcome for every input. And here's a formula that can be derived using conservation of energy and momentum. And this basically allows us to find the final velocities of an elastic collision when the second object has zero initial velocity. So for instance, if some mass m1 is traveling like this to the right and it's colliding with the another object m2 that's at rest, we can find the velocities of both objects using these equations. So m1 is traveling with velocity v1. So yeah. Okay. So now using these equations, I would like you guys to try example 3. And I'll give you guys a bit of time for this one because this problem is pretty tricky. I mean, not that tricky, but I'll give you guys some hints along the way. So I'll give you I'll give you 1 or 2 minutes and then I'll give a hint. Okay, so the first hint I'm going to give is the problem uses some special wording. It says a very heavy and a very light. So we're assuming that the golf ball is very heavy. I mean, the golf club is very heavy and the golf ball is very light. And what that allows us to do is allows us to approximate. So we can approximate the mass of the golf ball as 0 or the mass of the golf club as infinity, because 0 is very light and infinity is very heavy. So we can either let the mass of the golf ball be 0 and solve, or we can let the mass of the golf club be infinity and solve. So that's the first hint I'm going to give. And also note that in this equation, m1 is the mass that's moving and m2 is the mass that's stationary in this equation. Okay, so I see one answer. Okay, so some good answers I see. Okay, I'll give you guys 1 more minute to finish the problem. Yeah, I'll explain it. I'll let everyone finish, like try solving the problem, and then I'll explain it properly. Okay, so let's try this problem. We have a very heavy golf club hits a very stationary golf ball that's very light. And since we are told that the golf club is like way, way, way heavier than the golf ball, we can approximate it so that the golf ball has a mass of zero, because any object, so if you think about it, right, any number is infinitely times heavier than zero. Like 0 times infinity is still zero. So one is like way more heavier than zero. So if we let the weight of the golf ball be zero, then the golf club will be much heavier than the golf ball. And we're just approximating because we're told that the golf club is much heavier than the golf ball. And we also just want to the nearest integer. And since we know want it to the nearest integer, we are able to approximate since we're not given the masses. So that's why we're approximating the golf ball as zero, because we're saying that it's very light compared to the golf club. Okay, so now what we can do is we can just plug in the values of the masses of the golf ball and the club and their velocities into this equation right here. So the mass m1 is going to be the golf club, because in this equation, in these equations, m1 is going to be is the one with a non-zero initial velocity, and m2 is the one that's at rest. So in this case, the golf ball is at rest. So m2 will be zero. And we know that they collide elastically, so we can use the equation. We want to find the velocity of the ball. So we want to find v2, the velocity of the ball. And so we should use this equation right here. V2 is equal to 2m1 v1 over m1 plus m2. But we already know that m2 is 0. So if we plug in 0 into the equation as m2, we get 2 times m1 v1 over m1 plus m2. But m2 is 0, so it's just m1. And you see that m1 cancels out in the numerator and denominator because it's there twice. So the velocity of the golf ball will just be 2 times the velocity of the golf club. And the velocity of the golf club is 12 meters per second. So the velocity of the ball will be 24 meters per second. And yeah, so to reiterate, the reason why I approximated is because we wanted to find to the nearest integer. Like if the golf club was like 1,000 and mass of the golf club was 1,000 kilograms and the mass of the golf ball was 1 kilogram, and we plug this into the equation, we're going to get a number that's like 23 point something. It's like 23.99 something like that. And that's very close to 24. So that's why we are able to approximate. So does everyone kind of understand where I'm going, or understand how to do this problem? Okay, remember to ask questions if you don't understand something, because then I won't know when you guys don't understand, and I can like reteach what I'm trying to say. So don't be shy. Okay, so since no one has any questions, we can move on to the second type of collision. And this type of collision is called an inelastic collision. And this is the opposite to an elastic collision. So, oh, also, if you have a question, send it to panelists, because it won't let me open up Q&A when I'm screen sharing. So send it in panelists. Okay, so the second type of collision is inelastic collisions, and these are opposite of elastic collisions because inelastic collision is a collision where momentum is conserved but energy is lost. The formula? Are you talking about these two formulas right here? Okay, so these two formulas, they can be derived by doing conservation of energy and momentum. So if we write, like, I won't derive it here because we didn't go over energy, but I'll just like write it down for those who are interested. Um, so the initial velocity is going to be m1 v1I times plus m2 v2I, where I just means initial. And this is equal to, according to conservation of momentum, m2 v m1 v1f. So the final velocity for object 1 plus m2 v2f. So the final velocity for moment for the second object. So this is what conservation of momentum tells us. And we can also use conservation of kinetic energy to derive this because we know that kinetic energy is uh, conserved because it's an elastic collision, so it's conserved. So for those of you who don't understand where I'm getting this equation, the energy equation, just know that I'm going to be discussing this more in depth in next class, like what energy is. So it's fine if you don't understand this right now. So we have 1/2 m1 v1I squared, and we just do this for each term. So 1/2 m1 v1I squared plus m1/2 m2 v2I squared, so on and so forth, equals that. And also, we know that this only holds when the second object m2 has zero initial velocity. So this just means that v2I in our equation, the initial velocity of the second object is zero. So this term gets canceled out. And we're just left with two equations with 1, 2, 3, 4 variables. So this means that we can solve for 2 variables. And that's basically what we just did. We get a system of equations and we can solve each system for the 2 velocities, v1f and v2f. So that's basically what this is. Okay, does anyone else have any questions? Okay, so if there's no questions, I'll move on. Well, I was discussing inelastic collisions. So it's where momentum is conserved, but energy is lost. So and this is like the more realistic collisions, because when two objects collide, energy may be absorbed by the impact. When two objects collide, they make a sound, so energy is lost through sound. When they collide, it's released through heat. So a lot of energy is lost when two objects collide. And so yeah, this is the more realistic collision you see every day. And because energy is lost, we cannot use conservation of energy. So we only have the conservation of momentum equation. And inelastic collisions is basically where all of the rest of the collisions lie. So most of the time we'll be working with inelastic collisions because unless we're working in some ideal situation, we're always going to be working with inelastic collisions. And these aren't really special. This is just like what we call the other category of collisions. Because all we can do to solve these problems using inelastic collisions is just using conservation of momentum. So there's nothing special about these types of collisions. It's just the opposite to elastic. But there is one type of inelastic collision that is special, and these are perfectly inelastic collisions. Oh, where are elastic collisions used in real life? Okay, there are no elastic collisions in real life. Never, because energy is always lost in every single collision. It's impossible for there to be an elastic collision. However, whenever very little energy is lost, we can use elastic collisions to approximate something. So for example, I don't know if you guys know this, but there's something called a Newton's cradle. And I think if I search up a picture of it, you guys might understand. So Newton's cradle, if you just search that up, images. So it's basically this thing right here. And what it does is if you pull up one of the beads and then let go of it, it collides with all of the other beads and then shoots the next bead back into the air. And in this cradle, basically zero energy is lost. Like very little energy is lost. So we can just say that all of these collisions are elastic. So no energy is lost to them. So this is like a circumstance where we can approximate it as elastic, but in reality it's still inelastic. So elastic collisions will be used when very little energy is lost. Okay, so perfectly inelastic collisions. And these are collisions where when the objects colliding combine into one object. So when two objects are colliding and they stick to each other, that's a perfectly inelastic collision. And again, in this collision, momentum is conserved but energy is lost. And the reason why this is special is because when two objects stick to each other after colliding, they have the same velocity. Because like if two objects are stuck together and they move, they have the same velocity. So that's why this is like good. And this lets us basically, if you remember, we had the sum of the initial momentums is the sum of the final momentums. But since the velocity is the same, we can take the velocity out of the sum and we can put it in front. So we get a simpler equation where we have the sum of the initial momentums equals the final velocity times the sum of the masses. Okay, so let's try a problem talking about perfectly inelastic collisions. So if you guys could try example 4. I'll give you around like 4 minutes, I would say. Okay, remember to use conservation of momentum when trying the problem. So I'll give you guys a few more minutes to try. So remember, we want to find the initial momentum, the total initial momentum of the objects, and this will be equal to the final velocity times the sum of the masses. Okay, so I see some good answers. Okay, so let's try doing the problem. We have a Play-Doh, which is a sticky modeling toy. And all this means is that when we throw the Play-Doh at something, it will stick to it. So what this is saying is that this will be a perfectly inelastic collision. And so this Play-Doh has a mass of 4.2 kilograms, and it's thrown at a stationary rock of mass 3.8 kilograms with a speed of 10 meters per second. So let's just draw this really quickly. So we have some Play-Doh over here, and this has a mass of 4.2 kilograms, and it's thrown at a speed of 10 meters per second. And it's thrown at some rock, so some rock are here, and that's at rest. And then the two objects collide. So after the collision, it will look something like this. So we have this, and then it's stuck to like the rock like this, something like this. And then it will move to the right. And after the two objects collide, we want to find the velocity of the Play-Doh rock system. So we want to find the velocity of both objects after the collision. So let's first do this by finding the initial momentum of all of the objects. So the total momentum of the system before the collision will be, well, the momentum of the Play-Doh is 4.2, which is its mass, times 10, which is its speed or velocity, plus the mass of the rock is 3.8 kilograms, and its velocity is 0 since it's at rest, so times 0. So this is just 0, and this means that the total momentum before the collision will be 42 kilograms meters per second. And we know after the collision, the momentum will be the velocity of the objects times the sum of their masses. And the sum of their masses will be 4.2, which is the mass of the Play-Doh, plus 3.8, which is the mass of the rock. And I chose these numbers specifically so that we would get an integer answer. So we get 8. 4.2 plus 3.8 is 8. So we get the final momentum as 8v. And conservation of momentum tells us that this final momentum will be equal to our initial momentum of 42. So this is going to be equal to our initial momentum of 42. And if we solve for v, we get that v is equal to 21 over 4, or 5.25. So the velocity of the Play-Doh rock system will be 5.25. Okay, does anyone have any questions? Okay, so if no one has any questions, you guys can try the next example, example 5. And this is a bit harder. This is a bit harder of a problem. And because this is from the F equals MA 2020B exam. And if you guys don't know, F equals MA is a competitive physics exam, and it's pretty difficult. And this is problem 14. So don't worry if you don't know how to solve this problem, but I'm pretty sure just by knowing what perfectly inelastic collisions are, you guys should be able to solve this. So try it out and see how it goes. Okay, so let's try this problem out. And we're told that a large block of mass 5 kilograms is moving to the right at a velocity of 10 meters per second. Every meter, there are smaller initially stationary blocks of mass 1 kilogram. So let me just quickly draw the setup. We have some large block here, and so this is 1 meter, and then we have some smaller block, another meter, and then a smaller block, another meter, so on and so forth until infinity. So this just goes dot, dot, dot. And we want to find, we're also told that all collisions are perfectly inelastic. So every time the large block collides with the smaller block, it sticks to it, causing the larger block to slow down. And we want to find how far the large block will travel before its velocity decreases to below 3 meters per second. Okay, so we can use this conservation of energy, momentum here. We know that the initial momentum, it will be 5 times 10, which is 50, because the momentum of the large block is 5, which is its mass times 10. And all of the other blocks have velocity 0 at the beginning. So the initial momentum will be 50. Okay, and we know that this will be the momentum of the block and everything that's connected to the block, that's stuck to the block, will be 50 no matter what, because momentum will always be conserved. So we know that this 50 will be equal to the mass of the block times its velocity at any point in time. So let's see what will the mass of the block be when its velocity is 3 meters per second. So let's say this is 3 meters per second. So if we solve for the mass, we get the mass of the blocks will be 16.7 kilograms. And we just did this by using conservation of energy. So now all we have to do is find how far will the block travel until its mass is 16.7 kilograms. Well, we can do this by finding the number of smaller blocks that the mass gains. So first we have to round up. And the reason we round up is because if we round down, then the velocity will actually be above 3 meters per second. So when we round up, we get the mass is 17 kilograms. And so if we subtract 5 from this, because that's the original mass, we see that it must have gained a mass of 12 kilograms. And since each block has a mass of 1 kilogram, we must have gained 12 blocks. And then now we just need to find how far did the block travel so that it hit 12 blocks. And since we know that the distance between each block is 1 meter, the distance that the large block had to travel is going to be 12 times 1, which is just 12. So the distance that the block will have to travel is 12 meters. Okay, does anyone have any questions? Okay, so if no one has any questions, let's talk about impulse, which is basically the last thing we're going to talk about today, impulse. And the impulse basically allows us to find a relationship between force and momentum. But we must understand what impulse is before we can discuss force. And impulse, I don't think so that there are two meanings, but I might be wrong. So impulse, well, at least in physics, impulse is the change in momentum of an object. And it's denoted by the letter J. Uh, the only impulse I know is like when you push something like really fast, like a small quick force. That's what I would think impulse is. like other than physics, like when you push something really quickly. Okay, so in physics, impulse is the change in momentum of an object, and it's denoted by the letter J. And now that we know what impulse is, it's just a change in momentum. So we can relate this to force, because force is going to be the impulse over the time. And the time is the time that the force is acting on the object. And since impulse is the change in momentum, we can write this as delta P, or the change in momentum over T. And the delta, or like this triangle symbol, just means change in. So this is just change in P, or the change in momentum over the time. And we know the change in momentum is the initial momentum, so the final momentum, the PF, minus the initial momentum, PI, over T. So this will be the force on an object when its momentum changes. So let's try example 6. I'll give you guys 3 minutes to try the problem. Oh, the eye with the curve. Oh, that was just my bad. I was writing something else and then my mind just went. It should just be a normal eye. So, my bad. Okay, so we have a few answers. Let's keep them coming. Okay, so let's go over this problem. We have a ball of mass 5 kilograms. It's thrown at a wall and collides elastically. It has a velocity of 10 meters per second before the collision and collides for 20 milliseconds. We want to find the average force that the wall exerts on the ball. So the first thing we need to do is we need to find the change in momentum, or the impulse of the ball. And this will just be 2 times the mass of the ball times its velocity. And this is because the ball bounces elastically. So the velocity before the ball collides must be the same as the velocity after the ball collides in order for the energy to be conserved. So basically the momentum before the ball collision will be mv. And then after the collision, so when it bounces back, it's going to be mv in the opposite direction, so negative mv. And this means that the change in momentum will be 2mv or negative 2mv. The sign doesn't really matter. Okay, so this is going to be our impulse, J. And we know that the time is 20 milliseconds. And this is 20 times 10 to the negative 3, or 0.02. So if when we plug all of the values into this equation right here, we get that this is going to be equal to, or the average force will be equal to, 5,000 newtons. Okay, does anyone have any questions? Okay, so if no one has any questions, then I guess I'll wrap up the class for today. So if you want to read further on momentum, of course, Khan Academy is a great source. And then we have a few textbooks here with their corresponding chapters that you can go look at if you want to get a deeper dive in momentum. Okay, so yeah, that's it for today's class. Thank you guys for coming. And I'll see you all next week where we'll be discussing energy. So yeah, bye and thank you guys for coming. And I'll let Shomik be the host. So